Okay, and I guess we are live. Oh, you know what? I forgot to shed some light on this. And, of course, my plug is missing. Hold on. Oh, there it goes. Yay! Not quite as ugly. Well, still, oh god, that is terrible. That is terrible lighting. Terrible lighting. Okay, alright, hi everybody. Welcome to the Renaissance Builder. There's no viewers anyways. Oh, my lighting is terrible. Would this help? Yeah, a little bit. Alright, a little bit. Okay, so. Alright, so on this episode, this here live stream. Hi, Rupa. Hey, babe. Love you. Alright, so on this here live stream. Alright, so. If you guys happen to watch the last video that I actually posted, it wasn't a very long video. It was a short video about designing the circuit, or, you know, talking about the circuit that you see on your screen now. And I went to put this circuit together the other day, and I found out that it's a terrible circuit. Not because it doesn't work on paper, but because the components that are necessary for this circuit are very impractical. So, my intention tonight is to redesign it. And first I'll explain why this circuit is so bad. So what I'm going to do is I'm going to open up let's see, this, here we go. I'm going to open up the simulator. Why is this up here? That doesn't need to be up here. Oh, you're kidding me. You're kidding me. Okay. I love Windows. Love Windows. Alright. Exit out of this. I'm going to draw the simulator over here. And we're going to do it from scratch, I guess. Alright, new blank circuit. So, in order to explain why the circuit that we did create doesn't work very well, we're going to go ahead and create a new one from scratch in order to show why it doesn't work. Alright, we got a resistor, power source. I'm going to go ahead and set this up to 171.6 volts and 60 hertz. Okay, and I'm going to go ahead and start creating the rectifier. Now we are going to take this over here. This is going to be very sloppy. Yep. So if you're looking for something that's not sloppy, sorry. Literally just trying to get this, get the point made here. All right. Now, what I have is I set the resistances of the primaries to 1.5. Oop. Why is my phone's beeping at me? I don't know. Anyways, okay, so that was 1.5, and this was 1.5, 0.5. All right, so far we got the first half of the circuit. We have our resistors. Now, the point of these resistors right here is to drop the voltage across so that we don't have as much. I need it to be 5 volts. That's what I need. I need 5 volts. So in order to get the 5 volts now, I have one resistor here. That was 100,000 ohms, and that was the that's the circuit that drops. If you'll notice over here, that's this circuit right here. Oh, I only have that at 18, and this one at 100. Well, I changed that to 18 because this circuit right here doesn't give two hoots about amperage. It just needs to drop, but it is part of it. So now I need to trace this resistor, diode, capacitor over to this here. This is what I'm concerned about right here. The opto-isolator, 220 ohm, and that 1000 ohm. So let's pull this back up. And too many buttons. Yes. All right. Now I'm going to take a resist. I'm going to take a wire back over here. Nope. Sorry. I did that wrong. I'm going to go ahead and take a resistance over here. I guess I might as well do the diode and then the capacitor down to negative. And then I can do wire, take the wire here, take this over here, and I need resistor set 220 ohms. I'm just going to set this right here. Now I want to draw active building blocks, optocoupler right there. And I'm going to do the optocoupler. Ta-da! Need that too long. Alright. There. Alright, now let's see. In order to get my voltages correct, I want to make a voltometer right here. I want to make a ground right here. And then I'm going to put this in the scope. And we're going to watch it. Properties, take that down to 2 milliseconds. Alright, that gives a nice pattern there. Alright, so if you're designing a circuit, you'll notice we have a diode, which is a little superfluous. The point of the diode is to allow this circuit right here to maintain the sinusoidal wave pattern and then be DC on this side. That was the point of this diode. And then this resistor here was supposed to drop everything back down again. All right, I need to edit this to 220. Oh, not 1,220. 220 ohms. 220 ohms is a very common rating for LEDs. When you're on a 5-volt circuit, 220 ohms for an LED gives you about, I forget what it is, I think it's 10 milliamps, something like that. Perfect for an LED. And an optocoupler is an LED. So the input of an optocoupler is an LED. So that was the idea there. All right, now, this ripple right here that you see in the wave pattern, we're going to take that out with the capacitor. Let's check that up. I believe that was 1,000 microfarads, and boom. All right, now 7 volts. All right, I had that clamped to 5 volts with a Zener diode, so I guess I might as well draw that in there too. I did not give myself any room for the Zener diode. Active component, Zener diode. We're going to draw that right up here, and I'm going to have to redraw the wires to connect it. Now here's the thing, the Zener diode is going to pull Apparently too much. Let's reset it, see what it does. Taking forever to charge. It is taking a very long time to charge, yes. It should be about 5 volts. I believe the Zener diode is set at 5.6 volts. So the Zener diode should clamp this rail to 5.6 volts. And we're starting to level off at 4.7. Alright. So our circuit is pretty much doing what it's supposed to do now. Now let me explain why this circuit isn't going to work on a practical scale. The reason being is this resistor right here, whilst I'm getting the correct voltage, so on the DC bus, it looks right, it looks good, but looks can be deceiving. If I go over this, you'll see I have, if you look down at the, but oh, you can't see it, shoot. My face is covering the wrong thing. Let me take my face away. How about that? This one? Yep, there we go. Alright, so if you look at the bottom right screen, when I hover over the resistor for the LED, if you look at the bottom right where it says I, so it says resistor and then I, it is 22 milliamps. So 22 milliamps is actually really good. 22 milliamps is perfect for an LED. That's fine. I don't know if it's perfect, but it works fine. You can actually, in fact, I did look this up. The spec sheet on the opto isolator that I'm using, which is a 4N25, they want a max of 60 milliamps on the input. So 22 milliamps is perfect. So that's fine. That's not what I'm worried about. The power rating is 100 milliwatts. Again, perfect. But that's on that resistor. When I go to the other side, here's where it gets tricky. This, I'm going to have to put this in the scope. And you see a nice pattern here down at the bottom. So this is the resistor. This is the voltage drop and the current of the main resistor. Now, when I click on it, and let's see, I'm going to hit stop so I can measure it. I need the, alright, I'm going to show you, because again, my face is covering it up, alright, so you can see the bottom right screen. When I go over here to that resistor, 3640, it's already at 2 watts. 2 watts. Here's why that's a problem. I do have 2 watt. Oop, hold on. Let me turn the camera back on. So, I do have 2 watt resistors. I have a pack of 2 watt resistors. But that's not even the max that it's going at. So we have 41 milliamps at the max, right? And the voltage is 61. So if I take 61 times 41, that is 2,500, so 2.5 watts. The wattage that these resistors are handling is too much. Too many milliamps. And that's my problem. By the time I get all of this balanced out, the wattage on those resistors is really high. So I want to bring that down. Now, I may have messed something up here, so let's see if I can play with it a little more. I'm going to do a little bit of redesign, and let's see if I can play with it a little more, because that still isn't what I was looking at. So maybe I need to redraw this. So let's add the other components in. Okay, let's go with the, I need the, oh yes, op amp. Oh no, I want that to be out here a little bit. Let's give a little bit of room for stuff to happen. Okay, now I want a resistor coming to here and a resistor going to here. These need to be, we're just going to set these to, they need to equal 100,000. So I'm just going to do 50,000 and 50,000. Now the reason I'm using 100,000 is to decrease the amperage. We don't care. The comparator that we're going to be using doesn't work on amperage. It works on voltage. So I don't care about that. I need to redo this one again with the same. Let's see. Let me bring this wire all the way over to here. And I'm going to do the same thing. A voltage drop. Alright. And I'm going to set these up the same way. 50 thou and 50 thou. Okay, so that means I have two parallel resistances with approximately the same resistance. There is a series resistor in the second. I'm sorry. I have two series resistances in parallel. Yeah, that's why it drops it down to 50,000. That's why it increases the wattage. So in order to make that work right, I would have to increase the resistances to here if that is actually the problem. But I'm not sure it is the problem. So let's make that run again. And we're looking at stop 3.2 watt microwatt. That's not right. Run. Let's slow it down. And if I just watch it, milliwatts. Oh, damn, I'm not catching it. All right, I got to do the math. All right, we're at 41 milliamps, 61 volts. Still okay. So we're still looking good as far as that goes. 3 watts. I can probably handle 3 watts. It means I would need 3,000 ohm resistors would do the job to handle that. And of course, I don't have 3,000 ohm resistors. I'd have to make them a 1,000 and a 2,000. I mean, it's getting to be a bit of a bear to handle the wattage. It's getting to be a bit of a bear. Let's continue this diagram over, right? And I need a resistor down. I think it's about that close, and then I need to draw active building blocks, optocoupler. I got it right. Look at that. Okay. And this is 220. All right, now, if I can, nope, oh, I have to catch it at just the right time. But what I'm actually going to do is I'm going to bypass this here comparator. You can see that it turns on every once in a while. But I want to simulate it being always on to get my wattage. So I'm just going to bypass the comparator. Oh, It did not like that. It did not like that at all. Try it one more time. Simulator crashes. Reset. Run. Nope, doesn't like that. Got to get rid of it. Why? Maybe I'll just have to catch it in the act. Alright, reset and run. Get the speed up a little bit. Now I'm going to slow the speed down because I want to, got to be a little slower. I want to catch, missed it. I want to catch it when it's running. Okay, so I do have a different kind of solution here. Oh, I just missed it. I know what I can do. I can change the voltage. I am so bad at this. Alright, I'm going to change the voltage here. If I change this resistance, then the comparator will be on for a longer period of time. Try it now. Alright, so I do have a different solution. Alright, cool. Now I got it. Now, there we go. Alright, let me hide the camera and show you what... that doesn't even... Nope. Sorry. This is not showing me what I was looking at. And I'm not catching it, and that makes me kind of sad. 90 milliamps. Alright, so that's over... That's not... Oh, I apologize. I did something wrong. You have to edit this because they don't let you feed the appropriate voltages, the VCC and ground. They don't let you feed the VCC and ground of the comparator like you're supposed to. So that was wrong. Alright. Now, 2.4. I'm going to go ahead and watch the wattage on this. And 1 watt, 2 watt. Oh, it only goes a little over 2 watts. Maybe I was wrong. Maybe I can get away with just using the resistor drop on this circuit. Although that Zener diode sure is passing a lot of volts. I mean, a lot of current. So, let's see. In order to get that to drop further, I would need a greater voltage drop. Drop the voltage there. But that Zener diode is actually sized for this being on all the time. Maybe now this wire will... Nope, I didn't want it there. I wanted it here. Maybe now my bypass will work. Nope. Didn't like that. Alright. I'm going to have to reevaluate because my resistances, my wattage here is just over... It's just over like 2.5 watts. I might actually be able to get away with just using resistors. Excuse me. Just using resistors in this place. If I can get 3 watt resistors, then it seems like that should work. But I have another solution that is quite common. Ta-da! You can't see it. I know. All right, so this is a transformer. And it's actually a dual transformer. So on the one side, we got 110 volts in. On the other side, we have 2 8-volt coils. So 110 in to 8 volt coils out. That's if you put them in series, it's 16 volts at like, I think it's 1,500 milliamps. If you put them in parallel, it's 8 volts at 300 milliamps. So this is a nice little transformer that I can mount in here and drop the voltage via a transformer, which accomplishes two things. All right? The things that it accomplishes are two critical points that I have here. And let me show you the critical points. So I'm going to remove this scope, and I'm going to remove this scope. I'm going to put another voltometer here. And take this wire to there to ground the voltometer. I guess that was unnecessary. It just grounds to the ground here. Take that away. All right, now, let me draw this in the scope. Reset the scope down to 2 milliseconds. This pattern right here. This pattern that we now have on the screen is the voltage pattern you get after a full wave rectifier. So that's a full wave rectifier pattern. This is the pattern that I want on this side of the comparator. And if you want to know why, it's because I'm going to put another voltometer on the other side, and I'm going to add to the existing scope. All right, right here. Now it's coming across. Okay. You'll notice that I have two lines. The green line, so the green line and the red line. The green line is doing the sinusoidal pattern, rectified sinusoidal pattern. I need to raise that red line to a point that it's usable. Actually, let me drop that one. All right, so I'm going to take this to 75, and I'm going to take this one. The closer you bring the bottom side to ground, it drops the voltage. Or does it? I'm sorry, that did not do what I expected it to. Why did that not do? Well, now I'm just looking like a buffoon, I guess. That, yeah. There is odd. This should be 0. All right, let's do it further. Let's take it 1 and take this one to. Oh, I forgot the K. Sorry, my mistake. 25,000. So it was only a 75 ohm instead of a 25. 75 instead of 75,000. All right, now we have it set up right. 75,000, 25,000. We have a total of 100,000, but our voltage drops across here, so you can see our max voltage is like 10 volts. Now I'm going to go ahead and raise this voltage even higher. So we're going to take this to 10,000. What I'm doing here is I'm actually using these resistors as if they were potentiometers. Because this circuit simulator doesn't do potentiometers very well. All right, 90. So I'm just kind of doing it by hand, I guess. All right, so that raises our volts on the negative of the comparator is now 5 volts. And on the positive of the comparator, we have the sinusoidal pattern. This is the key. on a comparator, your input voltage is, or your negative voltage is a reference, and your positive voltage, so your negative is a reference, and your positive voltage, every time the positive voltage goes higher than the negative, the comparator turns on. And if the positive voltage is lower than the negative, the comparator turns off. And what it's really doing is it's kind of like a gate, right? So if you think of hot water and cold water, like your faucet diverts from hot water to cold water, right? So if you think of the comparator like a gate, and I've got hot water coming in VCC, which is your volts, I don't exactly know what it stands for, but you got your volt supply on your one side, and we got ground on the other. So I'm feeding it with 5 volts on one side and ground on the other. And then I've got my positive and negative inputs. My negative input sets the standard, and whenever my positive input goes higher than negative, it turns to hot. Whenever my positive input is lower than negative, it turns back to cold, right? So I'm either applying source voltage or I'm applying ground to the output pin. That's the comparator. So if you'll notice on this wave, every time my reference voltage is the red line here, and it crosses at this point right here on the screen. So if you're looking on my asterisk on the screen, it crosses that point where it goes, it turns off right here, turns on right there, turns off right here, turns on right there. The entire point of this circuit is so that I can change that reference and cause the comparator to turn on and off where I want it to on sine waves, the entire point. That being said, all that designed, everything is actually working. I can actually drop my, it looks like I can actually drop the positive input a little bit further so that my negative input can actually reach the peak, but this works. And with this, I am running 2.5 to 3 watts on that resistor. This one is running 1 watt, little over 1 watt, so that resistor would be fine. And in fact, I could probably upgrade that resistor a bit, because I think the capacitor is, I don't know. If I raise that resistor to drop the wattage, then it charges the capacitor slower. And it's pretty well balanced right now, so that doesn't necessarily need. And this one, I could probably do this if I got 3 watt resistors. So this circuit would probably work. However, if I want to do it even more different, I have this here control transformer. So I can put in 110 and get out 8 volts. But it's 8 volts RMS, 8 volts sine wave, so that this circuit would still work, but I don't need those 2 resistors. I would just have the transformer. So I guess it's kind of it's a give or take, right? So if I use the transformer to drop the volts, so let's just see what that does, right? We're going to go ahead and erase some of this circuit and change it to 8 volts and see what it does. So I'm going to go ahead and edit this. And all right, here's what you do. Excuse me. I forgot to put on my microphone this whole time. That is fantastic. And nobody told me it was too quiet. All right, so if you're going from RMS and you want to know the peak voltage of an RMS circuit, what you do is you take your volts times 1.43. Wow, this calculator is absolute crap. That thing's garbage. Excuse me. Getting dried out. Getting dry throat. Guess that means I'm talking too much. All right, so I'm going to take 8 volts times 1.43, and I get 11 volts. So 11.44 volts. So I'm going to go ahead and set this to 11.44 at 60 hertz. All right. Excuse me. Oh, wow. Now I'm going to change the resistors. These main resistors. I'm going to take them down to pretty much... Can I take them down to 0? I don't know if it'll accept 0. Close enough. So I'm going to drop that down to minimum. Now, again, these, that works. All right, so let's hit reset. It looks like our sinusoidal pattern, which is doing very well, is max 2.57 volts. I can actually raise that because we're going to get 5 volts out of... It's taking forever to charge, but we're going to get 5 volts out of that. So I'm going to go ahead and change this back to 50 and 50 to give it a good middle of the road. All right. Oh, 5.16. Perfect. Now, we may have to adjust our capacitor and resistor levels. Yeah, this resistor is now doing too much. So let's drop this to 500. 500, not 500,000. Compare. Yeah, I want this up to 5 volts. Now, Sergeant Coombs actually gave a solid recommendation to use a 5-volt regulator in place of all this. And a 5-volt regulator, the 7805 5-volt regulator, is limited to a 36-volt max input. At a 36-volt max input, I would have to redo the resistances. You wouldn't be able to feed it. But it would work on this circuit. This circuit, it would work perfectly fine with the transformer. So if I have the transformer in there, a 7805 to take the place of the capacitor, all this stuff would work perfectly fine. And it would eliminate the need. What's going on here? That's all right. So let's take this down even further. In fact, let's just see what happens if I take it to 0. Oh, it's going over 5 volts. Oh, that is doing weird stuff. It's going over 5 volts by a lot. All right, so we definitely want it in there. All right, now we're coming back down. And you can see that everything's working. Now, if I go to here, I never go above milliwatts on that resistor. This resistor stays at maximum 16. It never goes above 20 milliamps. So that works out correctly. And everything's adjustable. So, ta-da! In fact, I could even let this, it's down to 4 volts. I could even shrink this a little more. Let's shrink it a little more. Let's go to 200. And see what it does. Should increase, this voltage should increase right here. not by much. All right, let's try 100. Basically, I don't want this to go over 5 volts. And it won't, because I have it clamped with a diode there, but... Alright. 100 ohms. Looks like it's the ticket. I'm going to go ahead and change this. Create a new simple model, and I want the breakdown voltage to be 5.1. Okay. Alright, yep, there we go. It's clamping it. Ta-da! Now, what happens if I take away the drain? I got this wire right here. Let's go ahead and, if I take away the drain. Alright, so when I take away the drain, you can see that I do get more past the Zener diode. What's my wattage here now? Picowatt, milliwatt, picowatt, milliwatt. Alright, that still looks okay. The wattage on that is never goes above milliwatts. This never goes above milliwatts. That looks like it's working. Cool. Add the wire back in. And that's about 20 milliamps. Perfect. So that circuit is working great. So if I use the transformer, then all my resistors, I can use 1/4 watt resistors for all of it at that point. That's fantastic. I should probably make sure, because 1/4 watt's going to be 250. Not necessarily. I'm going to put this in the scope, and then I'm going to hit stop, and we're going to do the calculation. So I'm at 44 milliamps, right? So that's 44 milliamps, 44.3, and multiply that by 4. Wow, really? It really drags down the voltage. 4.43431 volts equals 196 milliamps. So 196 milliamps. That's less than 1/4 watt. So I don't see any reason why this wouldn't work perfectly fine. Interesting that brings the... Oh, it's drop. That's how much volt it's dropping. Sorry. If I measured it against here, this probably isn't dropping nearly as much volts. And this is what the actual total voltage is. So when I click on it, it's voltage drop. All right, so this is the circuit that I would use with the transformer for sure. Now the circuit I would use, and if I don't use the transformer, then I have to use 3 watt 1.5 thousand ohm resistors. May get the job done. So yeah, all right. This has been 45 minutes of shooting the shit designing circuits here, and with barely any viewership and 1 comment, because this is new and it's fun and terrible all at the same time. Anyways, if you are watching on the video after the live and have gotten to this far, I appreciate it. Thank you very much. Feel free to leave a comment with suggestions and what you feel like would make this actually a little more interesting, and you know, however it works. So yeah, I didn't announce this or anything, so it doesn't surprise me. I got like 3 views the whole time. Yeah. But anyways, thank you very much, guys. Gonna be doing more of this. Gonna be doing a lot more of this. Well, not necessarily circuit designing. We'll be doing circuit designing for sure as part of the live streams. But this is all part of you know, the behind the scenes, doing the projects. We're working on some very interesting stuff. And this is all the behind the scenes of doing that stuff. So that's what it is. Thank you very much, everybody. I guess I'll see you in the next one. Have a good night.